So when you go live, what are people watching exactly? Your screen?
My screen. So I'm sharing the screen of Google Meet. That's the screen they see. So I have to be careful of what I do there, like putting up some menus and stuff like that I cannot do. So that's okay. I'm gonna check what's going on YouTube now. Okay.
So when you go live, what are people watching? And Chris, just in case you were talking to us, you're muted. I saw you.
Yeah, no worries.
Okay.
I'm sorry to interrupt, Diego Gutiérrez. El estudiante al que has cancelado antes de la llamada dice que ahora no le permite unirse.
I'm sorry, but esto es un problema, porque es que no podía dejarle entrar antes. Entonces,
vale, perdona, ha sido tú, Julio, perdona.
Sí, he sido yo porque estamos hablando de otra cosa. Sorry, Katie, for the Spanish thing.
Maybe he can move to YouTube.
He can move to YouTube. Sorry about that.
Okay.
Tell him that we're sorry, but yeah.
Right now, I'm afraid.
Okay, some people in.
While the people continue joining, Katie, thanks a lot for accepting Diego's invitation. We are very happy to have your seminar in the Masters.
Oh yeah, thank you. As I was saying, I'm really honored to have invited to give the first talk of this new program. So that's pretty exciting. And Diego and I had emailed throughout the year a little bit, and we were hoping to have something in person. But hopefully, in the future, we can still find some time to meet in person.
We will. Yeah.
Yeah, this cannot continue forever, right? So hopefully we can have seminars in person at some point.
But the good thing of it is that then people can easily kind of call in from different parts of the world. So like this was nice for my class last quarter. I had some invited speakers that I wouldn't have been able to have otherwise join in.
That's true.
Same.
Yeah, the only problem with you being the first is that it's going to set the bar so high that there's no way we can maintain this level of speakers. So all of you students don't expect this every other week. So Julio, I'll leave it up to you whenever you're ready.
There's 44 people on Google Meet, and there's another 15 people going up on YouTube. And Katie Bouman is sharing her screen now, and I'm gonna share. Okay, let me check. Okay. Okay. I'm just double checking that everything looks good in both sides, in Google Meet and in YouTube. Okay, it looks good. Maybe we should wait maybe a couple of minutes more, but just in case. I don't know how many master students are here, because there are people that are not from the masters too,
but 45 people here plus YouTube people, that sounds about right. So
yes. Yeah, Julio, if you want, I can check the YouTube streaming, and you can focus on this one. So
I have two screens, so I'm fine. But if you want to check the YouTube,
perfect.
Fine.
You have two screens and live. Perfect.
I have one screen on the right with the YouTube, and then the other one with the
awesome.
full screen with. Okay, so we probably should kick it off now. Welcome everyone to the first seminar of the course. I'm Julio Marco, one of the teachers of the course, along with Adrián Jarabo and Ana Cris Murillo. And today we're having an awesome talk by Katie Bouman that Diego will be introducing a bit later, but let me just start by setting a few comments about how this is going to work. There's, as you know already, there's the presentation is going to happen on Google Meet, but there's also, in case you have any problems with the connection, there's also streaming happening on YouTube. You have the link on the webpage of the course. I will gladly ask everyone that you turn off the cameras and you turn off the microphones as long as the presentation is going. We'll have a final session of questions at the end of the talk. You can write down your questions on the chat either on Google Meet or on YouTube, and we will just select questions from one side or another, first come, first serve. And if there's questions that are common or they share more or less the same concerns, we'll probably mix them together. And it will be nice if you can also say your name and your role if you're a student, but that's pretty clear that you're in the master's, but there's probably people on YouTube that are not external to the course. So when you say a question, it's great that you say your name and where you come from. And I think that's pretty much everything. I think I'm not missing anything interesting. There's some more people coming in.
No, just don't be shy asking questions. There
Yeah.
will be plenty of time. So chat as you hear something that may trigger a question. Don't wait until the end necessarily. Everything will be buffered, and then we'll go through all the questions. Don't be shy.
Yes, we'll have like around 50 minutes talk, and then we'll have like half an hour or even longer for questions. So, okay, so we'll just leave it to Diego, which is the person that invites Katie, and will be the one doing the honors.
So thank you, Julio. So for me, it's super great that Katie Bouman is here finally, after we've been trying to visit each other for over a year, and then COVID happened and there went all our plans. So I'm super excited about this day. I'm very honored that she accepted the invitation to be the first talk in this series of seminars. Professor Katie Bouman is a Rosenberg Scholar and an assistant professor in the Computing and Mathematical Sciences and Electrical Engineering Department at Caltech. Before joining Caltech, she was a postdoc fellow in the Harvard-Smithsonian Center for Astrophysics, and she received her PhD in the Computer Science and Artificial Intelligence Lab at MIT. Before coming to MIT, she received her bachelor's degree in electrical engineering from the University of Michigan. You all know her for the black hole imaging result. The focus of her research is on computational imaging, which is, as you know, a course that you will be learning about in the second semester. So, as I said, very excited to have you here, Katie, and all yours. Thank you.
Thank you so much for the kind introduction. Yeah, I'm so honored to be the inaugural speaker of this new program, the Robotics, Graphics, and Vision group here. So thank you again for inviting me. So yeah, so many things that we wish to take pictures of, we can actually see with our own eyes. And using a standard camera, we can take a picture that looks like the scene that we can see with our eyes. It might be slightly blurrier or noisier than we'd like, but still roughly that targeted scene. But in many cases, what we want to image is actually invisible to us. So for instance, you can't take that camera and point it at our head and then get a picture of our brain. And so in these cases, it's impossible to directly image the thing we want to see. And so we have to develop alternative ways to take indirect measurements. For instance, by using an MRI scanner. And in these cases, the measurements we make don't look anything like the image we're trying to capture. And so we have to design algorithms that work with the new sensing system in order to recover the desired picture. And so as Diego said, this class of problems is called computational imaging because we're adding computation into the imaging pipeline. And in a lot of my work, I've worked on applying this methodology in a number of different kinds of domains. So like I've been working currently on imaging earthquakes, starting to get a little bit into studying clouds, did some medical imaging and stuff. So I really like this idea of joining computation into the sensing system pipeline. But today I'm going to focus mostly on telling you a little bit about how we've been able to use this methodology to reveal what I think of as the ultimate invisible, black holes. So black holes are one of the most mysterious objects in the universe, and scientists have been studying them ever since they were first predicted by Einstein's theory of general relativity just over 100 years ago. And in particular, for decades, scientists have been studying the giant elliptical galaxy that's at the head of the Virgo constellation. So this galaxy, which is called M87, is really special. It's 55 million light years away, and over 100 years ago, someone discovered a streak of light on the sky, which ended up being this galactic scale jet of plasma that was shooting out of the core of the galaxy and marking the spot of a supermassive black hole. And so over decades, scientists have tried to develop better and better instruments to try to study the supermassive black hole predicted to be at its center. And then in April of 2017, we hooked up this Earth-sized telescope and collected the data necessary to make the very first picture of a black hole. And this is what we saw after 2 years of processing that data. So this black hole image was the result of hundreds of scientists and engineers from around the globe that worked together to build an Earth-sized telescope that was necessary to take this image. And so today I want to tell you a very abridged story of how we were able to capture a picture of a black hole. And there are many angles to this story, so I hope to give you a glimpse in my primary contribution to it, how imaging was done and how we validated that image. And then in the second half of the talk, I'm going to talk a little bit more about techniques that are currently being developed in my group at Caltech to push this telescope past its current limits and to see more and to study more about black holes. So in particular, I'm going to be talking about new methods my group is working on for doing uncertainty quantification of the images. So understanding where we're unsure and efficiently understanding where we're unsure about the images. And also how we're developing machine learning methods to optimize the placement of the next telescopes we build into this Earth-sized telescope array. So the first question you might ask is, how are we able to take a picture of a black hole that by definition doesn't let light escape, so it should be unseeable, right? Well, light propagating near a black hole doesn't follow straight lines. It's curved because the black hole is curving space-time. And so photons can even go in circles around it. And so the space around a black hole is lit up by this hot gas that's spinning around. It's heated to hundreds of billions of degrees, so you have these photons flying around everywhere. And some of the photons fall into the black hole, but other ones just graze it and are bent by the black hole's gravity. And the net effect is essentially that the black hole casts a shadow on a backdrop of hot material that's almost perfectly circular. And if Einstein was right about general relativity, this light would be bent into a ring whose size and shape tell us about the mass and the spin of the black hole. And this ring is often referred to as the black hole shadow. So here is a more realistic simulation of what we would expect to see if we could see the black hole up close with around a 1 millimeter wavelength. And so these simulations are done by computational theorists, basically the computer graphics people in physics departments who try to ray trace what it would look like around a black hole. But it turns out that even though we can see this imprint of the black hole on the backdrop of the hot material, taking this ring is still nearly impossible. And that's because this ring is incredibly small. It's about 40 microarcseconds in size, which is about the same size as a grain of sand. But when that grain of sand is in New York, and I'm viewing it from California. So that's a really, really tiny, and taking a picture of something that small is really difficult. And the reason why all comes down to the limits of diffraction. And so diffraction says that if we plug in the wavelength and required angular resolution necessary to see that black hole shadow into this diffraction limit equation, we can calculate that in order to see the ring, we would need to build a telescope that's 13 million meters across, or essentially the size of the Earth. And if we could build an Earth-sized telescope, we could just start to make out that distinctive ring of light that's indicative of the black hole's event horizon. And so although building a single-dish telescope the size of the Earth isn't possible, by joining telescopes located around the world, I've been working as part of the International Event Horizon Telescope Collaboration that built a computational telescope the size of the Earth, capable of resolving structure on the scale of a black hole's event horizon for the first time. And so the EHT is composed of telescopes from around the world that were originally built for other purposes. Actually, one of these that was used in the 2017 observations was in Spain. And by installing specialized equipment at each of these sites and linking the signals through the precise timing of atomic clocks, we've been able to make these originally disjoint telescopes work together. And so teams of researchers at each of the telescopes essentially freeze light by recording petabytes of data, and then our computers process the data and act like the lens to make the picture. And so my primary goal in the project was working on constructing an image from the data that was taken from these different disjoint telescopes. And so how do we go about doing that? Well, unlike with a regular camera, in the Event Horizon Telescope, or EHT as we call it, we don't capture the picture in pixel space, but instead in its frequency space. So we essentially take measurements of the black hole image's Fourier transform. And if we put telescopes all across the globe, we would sample all these spatial frequency measurements. But since we only have telescopes at a few locations, that means we only get a small number of measurements. And so it turns out that for every 2 telescopes in the array, we obtain a single complex measurement of the underlying image's 2D spatial frequency that's related to the projected baseline between the telescopes. Each of these measurements is complex, so it's described by the 2 numbers, amplitude and phase, which is going to come in handy later. And so in 2017, when we took that data, we had 8 telescopes, but actually of those 8 telescopes, only 5 of them were able to see M87 and were at different locations. So then that would be only 5 choose 2, only 10 points that we'd have to try to make an image from. But luckily, as the Earth is rotating, we obtain other new measurements. So because the baselines between telescopes change as the Earth rotates, that projected baseline changes, this amounts to carving out different elliptical paths in the spatial frequency plane. And so how do we make an image after extracting these measurements? Oh, I'll just say also, so when you have telescopes that are close together, that's going to be a short baseline. So that's going to give you about broad structure in your image. It's going to tell you low spatial frequency. And so to get the detail, we need to see the ring. That's why we have to put those telescopes far apart. Okay, so at this point, we have the data, and we can kind of abstract away the astrophysics of it and look at it as simply a mathematical problem. We have this sparse data, and our challenge is to find the image that caused it. And if we were given measurements that covered the entire frequency plane, this would be trivial. In the case of no noise, you would just simply need to apply the inverse Fourier transform to the measurements. But since we only see a few measurements, that means that there's an infinite number of possible images that are perfectly consistent with the data that we measure. And on top of that, there's a different, quickly changing atmosphere above every telescope across the globe, which causes our data to be really noisy and makes the problem even more ill-posed, even more challenging. And so I like to give an idea of what this noise looks like because it informs how we go about the reconstruction task. So the whole reason that the Event Horizon Telescope is able to work in the first place is due to the fact that light from the black hole is going to travel to Earth for 55 million years, and then it's going to reach one of the telescopes slightly before the other one. And this time delay is key for extracting that spatial frequency measurement that's used for image reconstruction. But when you have a telescope in Chile, and one in Hawaii, and one in Spain, they all have different atmospheres above them, and each atmosphere causes a random delay in the received signal, which leads to an additional random phase delay in each frequency measurement. And similarly, the atmosphere also causes a different attenuation factor in the signal, causing a changing absolute gain term. So this error is very challenging because ideally we would measure this Fourier component, the italicized V here, this nice, beautiful Fourier component that we could use to recover an image. But in reality, we have a completely random phase error, which rotates that phasor, right? And sometimes a pretty bad amplitude error as well. And so this is pretty terrible because at first glance, we've lost both our amplitude and our phase information. And so if you've lost both amplitude and phase, what really do you have left? But if you look at this measurement term, you'll notice that the corrupting terms are actually site-based. They occur at every telescope. And every measurement is coming from 2 telescopes. So that means that if we have a third telescope, then the measurements that are formed with that third telescope share some of the same corrupting terms, G2 and Phi2 here. So we can design imaging algorithms that take advantage of this redundant corruption when solving for our images. So essentially, we solved the constrained phase retrieval problem, if you're familiar with phase retrieval. So to do this, we developed 2 classes of imaging algorithms to tackle the problem. The first class of algorithms is based on a very standard method used in the radio interferometry community, and it's called clean with a self-calibration loop. And this is a very traditional method of making images within this community, which made it a plus because it was well understood in the community, and people have a lot of faith in it in that community. But the disadvantage is that it was originally designed to work when you have more telescopes or when your noise wasn't nearly as bad as the noise we have for the Event Horizon Telescope data. So when you're using this kind of approach on the EHT data, you often need a lot of guidance from a knowledgeable user. A second approach is a class of methods we've been developing more recently called regularized maximum likelihood methods, and these are based on more of a Bayesian style approach. And in this method, we don't try to find an inverse function that takes us directly from the measurements to a picture, but instead we try to find a picture that both fits the measurements and is what is defined as likely through some sort of image regular or prior. And so the disadvantage here is that we have to mathematically define what is a likely image, and that is going to introduce bias, and it's also very unclear what a likely image is, right? We've never seen a black hole before. But the huge advantage of these methods is that we can naturally incorporate other types of errors. So for instance, we can directly try to optimize an image with constraints that are insensitive to the types of errors that I described earlier. They cause the errors to kind of cancel out in a cool way. And so by solving for the image that best fits these kind of new data products where which is invariant to these errors, we can find an image that best fits these measurements, but also looks like how we expect images to look. And using this, we can whittle down from the infinite possibilities to one that we think is a likely image that fits the data well, even in the presence of crazy noise. And I do want to highlight here that I'm talking in terms of likelihoods and priors, but in reality, we're solving a loss that is inspired by a Bayesian estimation framework. We have a term that describes the data fit and a regularize it that penalizes bad-looking images. Okay, but note that even if we develop these methods to recover an image, a single image, we have to be really cautious because any method we come up with, whether it's a traditional approach, this more Bayesian style approach, or a fancy new machine learning approach, it's going to require that we inject some additional information into the problem about what images look like to recover something back in the end, to choose among those infinite possibilities. And so that's always going to bias your final picture. It'll just bias it in different ways. And so, for instance, we wouldn't even want to accidentally have a preference for ring images, and then be super excited that we recovered a ring back in the end. So we had to be very careful when imaging that we understood these biases and made sure that they weren't affecting our scientific conclusions that we were making. And so that meant the big question we faced in dealing with the M87 data is not just how to make an image, but how do we verify what we're reconstructing with our imaging algorithms is real? And we tackled this through a multi-step process. In the first step, we wanted to avoid shared human bias to assess common features among reconstructions that were done under different kinds of biases. And so we split ourselves into teams. So we split about 40 people who worked on imaging. Either they developed methods or they're just very experienced at using these methods, into 4 different teams that span the Earth. And these 4 teams were not able to talk to each other at all during the imaging process. And they worked in isolation, trying to make their best image from the data for 7 weeks. And then after 7 weeks, we all gathered together and we revealed the images to one another. And this is what we saw. So to me, this was really amazing because although every picture was different, they were all done with different kinds of methods, and different people who had different biases were doing them, but all of them still recovered the same basic structure, this ring of roughly 40 microarcseconds in size that was brighter on the bottom than the top. And so seeing these images was one of the happiest moments that a number of us had in the collaboration, because it brought a whole other level of confidence to our results, as we found the same structure no matter what person or method reconstructed the data. But just because we had avoided shared human bias, that didn't mean that we were avoiding human bias altogether. So we spent the next couple of months essentially trying to break our images. And that led to the second step, where we tried to objectively choose image parameters and remove humans from the loop as much as possible. And to do this, we developed 3 different imaging pipelines. You can download these pipelines along with the actual M87 data online. It's on the EHT website. And so you can run these methods yourself or develop your own new approaches to get better images. And all of these approaches, though, have their own individual knobs or hyperparameters that are usually tuned by a human user. But instead of having a human tune them, we instead wanted to search for the best set of knobs to recover different kinds of source structures and see how that affected our results. So for instance, we generated synthetic data as if the Event Horizon Telescope were actually seeing a disk on the sky with no hole in the center, and then we found the best parameters to recover this disk shape. And then when we transferred these exact parameters onto the actual M87 data, although we had tried our hardest to find parameters that would best recover a disk with no hole in the center, we found that our data and methods required us to put that hole in. And by doing this simple training and testing procedure on many different types of underlying sources, we saw that our methods always preferred this ring shape, and that was true no matter the day we observed M87 on or the imaging code that we used to reconstruct it. And so by blurring the images from different imaging pipelines to an equivalent resolution, we then averaged them together to form the image that we showed the rest of the world last April, this ring of light surrounding the black hole, roughly 40 microarcseconds in size, and brighter on the bottom than the top. So although we had then gotten this image without trying to tune these knobs ourselves, we still weren't kind of sure. And so we went through a number of validation tests. We did a lot of these. I'm going to talk very briefly only about one of them, but you could look at our papers for the additional tests and details. So previously, I talked about how we selected one set of parameters, this beta here, that performed best on synthetic data. But why should there only be one parameter set that we consider? In fact, by doing large parameter surveys, we found that there are many parameters that actually perform reasonably well. And so rather than just selecting one beta, we instead selected a threshold and found all parameter settings that performed better than that threshold on the synthetic data. And then we could apply those to the M87 data and see the variations that occurred. So for example, for the HT imaging pipeline, we ran about hundreds of thousands of simulations, and we found we had about 1,500 parameters that we decided were acceptable. And so, for example, here's a slice of two of those parameters that we searched over, and the green boxes show a selection of the images that were identified as reasonable through tests on different synthetic data. And so once we had these images, as I said, the 1,500 for one of those surveys, we could look across them for variations. So the standard deviation tells us where those deviations were. So you can see that there are these certain kind of knot regions along the bottom of the ring. But if you look at the value of the standard deviation and compare it to how bright that ring is, you'll notice by looking at the fractional standard deviation that although there is some regions along the ring that we have more uncertainty in, that ring appears in basically all our images. And what we don't have a lot of faith in is all that wispy structure on the outside of the ring. So you shouldn't believe all that kind of stuff. But our goal then is to use this image, right, to extract science. That's originally why we are taking this image. We want to learn about black holes and gravity and to extract some understanding of science. So we can characterize so it's important to characterize this uncertainty because we want to characterize the uncertainty in image features that lead to science deliverables. So for instance, we could use simple methods to recover the ring diameter. So we just use simple ring fitting algorithms. And once we do this for all images, we can compare the diameters we get across different images with different beta parameters and also across different days. And we found that across different methods and across days, we had a very consistent parameter, a very consistent size of the ring diameter, roughly 44 to 42 microarcseconds, that was invariant to all these different kind of parameter choices, modeling choices. And so this is another way that we can become confident in the size of the ring we're recovering. But I do want to strongly highlight that what we were doing here was probing different modeling choices and seeing how that affected our results. So in the regularized maximum likelihood problem, we're essentially changing something like our prior turn and seeing how that prior affected our results. We changed other things, but that was the main kind of thing that we were probing over. And that's definitely something that's important to explore because we do have uncertainty in what that prior should be. But it's important to note this is not a posterior distribution. So what I was showing before with the uncertainty is not a posterior distribution. So going forward, it would be great if we could efficiently explore uncertainty, not only due to the prior, but also due to the data fit. And so in other words, we would love to be able to sample from our posterior distribution directly. under kind of prior assumptions and see how that affects our results. But how should we do that? Well, one natural approach would be to use a Markov chain Monte Carlo method, a MCMC method. And we have done some of this. So for instance, we didn't just estimate the diameter of the ring from the recovered images, we also did direct crescent or ring models. We fit these directly to the data. And so this simulation is showing an optimization of a sampling framework where it's trying to fit a simple crescent model to the data. And when you do this, you also get a ring of roughly 40 to 42 micro arc seconds, which was very consistent with our imaging results. But using these sampling methods, we get something more, and that's that we get a posterior over these kind of ring parameters. However, the catch is that this is only fitting a few parameters of the ring. There are a very few number, less than 10 definitely, parameters that we were fitting. And so it's very challenging to scale up some sampling approach like this to capturing posteriors of images that are very high dimensional. And so to tackle this, we've been developing new methods for efficient posterior exploration. So this is a bit of a tangent, a bit of an aside, but I wanted to sneak it in there to show you some more recent work that's going on in my group at Caltech, and hopefully how it will lead into future results from the EHC. So variational methods are a widely used approach to approximating intractable posterior distributions. And in a variational method, instead of directly computing an exact posterior, these methods say, okay, let's say assume that there's a simple family of density functions. For instance, this family of Q theta here, a family of distributions Q theta here that's parameterized by theta. And we want to solve an optimization problem to find the parameters theta that best match a target probability distribution. So if this ball represents the space of parameterized models, we might approximate the posterior distribution indicated by the yellow star with the model parameters theta star. And the traditional way that these models are optimized are by minimizing the KL divergence. And the KL divergence is a measure of how one probability distribution is different from a reference probability distribution. So let's try to find the theta that best matches that distribution. So here we're saying we want to find the parameters theta of this family of distribution Q that best matches that posterior distribution. And here I'm just writing out the definition of KL divergence. And you'll notice that it integrates over two terms. The first term is the probability of a sample image X under your proposed variational distribution. And the second term is a probability of the image given the measurements. And using Bayes' rule, we can write out this probability in terms of the data likelihood and the prior on the image X. And simply rewriting this as an expectation instead of the integral, we can see that minimizing the KL divergence just comes down to an expectation over the maximum a posteriori loss from earlier that we were using. But we just added, all we were doing is adding an entropy term here on the end that encourages entropy on the variational distribution. And that's interesting because the first part just looks exactly like we were optimizing before with those Bayesian-inspired regularized maximum likelihood methods we used for imaging. But now we're just including an entropy term that basically is discouraging us from collapsing to a single solution. And if we find this theta here, then we can sample from Q theta to see roughly what the posterior samples look like. But then the question becomes, what should this family of variational distributions be? Well, traditionally, they were typically pretty simple. So you could solve these integrals by efficiently evaluating probabilities. But it would be great if we could use a much more flexible family of models that is able to better match the posterior distribution and get closer to it. And so this is something that my postdoc Hassan and I have been working on recently. And so the question is, what should that more flexible family of models be? And so I'm sure many of you are aware that deep neural networks can do this amazing job at modeling complex distributions. And for instance, you can train a neural network to take an image of noise and output a picture that at first glance looks real. And by plugging in different noise images, you can get different output pictures. And so these networks are essentially sampling from a very complex and implicit distribution over the space of images. And these deep generative models do a scarily good job at generating samples from high dimensional distributions. And so, for instance, you can log on to this www.whichfaceisreal.com and try to guess which image is a fake image and which one is a real one. And although there are some artifacts you might be able to pick on, it's pretty amazing how realistic these images look. And so for the neural network to do this, it had to be incredibly flexible in order to model all these different correlations in the distribution of real images. Just in case the one on the left here is the real one. And so why don't we use this distribution, this neural network defines implicitly as our variational distribution Q, and solve for the parameters of a neural network to best approximate that posterior. And so this is a kind of a neat idea, but the challenge is that for an arbitrary neural network, just because we can sample from it doesn't mean we have a way of evaluating a probability of that sample, which is necessary for doing this optimization of the KL divergence. But if the neural network were invertible, then we could actually calculate this probability. So maybe we can try to use an invertible neural network to define a family of variational distributions we want to search over. And we do that through a certain class of special networks that's gaining more popularity now called flow-based networks or normalizing flows. And these are certain networks that are invertible, whereas most generative networks that you hear about are actually not invertible, but these ones are, and so they allow us to estimate the probability of each of our image samples X. And so using this, we can define a method for training a variational network to sample from the posterior distribution of images, and we call this deep probabilistic imaging, DPI for short. And what do we do exactly? Well, we solve for the parameters of flow-based neural networks under this divergence loss, and so we just plug in the likelihood and prior constraints just like we were doing before. So those first two are just the exact same optimization problem we were solving before, but we also add this thing at the end, though, for the entropy term. And notice that for this, we don't ask for any training data. So this is not like training a network in the traditional way where we use supervised learning and then we can sample from that network afterwards. We are simply training a network under the loss of the current data and prior constraints to approximate this well-defined posterior. And then to generate samples from the posterior, we simply need to sample from this learned generative model, which is really quick and easy. You just plug in you sample random noise, plug it through the network, and you get different posterior samples. So how is this helpful for characterizing the solutions of a realistic black hole data set? Well, here's an example. On the top is a synthetic image of a black hole, and the same image to the right of it is blurred, but it's blurred to the resolution that we'd expect to be able to achieve with a radio telescope. And we took this image and we generated synthetic data from it, as if the Event Horizon telescope were seeing this distribution of flux on the sky. And this was actually a data set we had identified, we tried testing ourselves on years ago. And when we ran our regularized maximum likelihood on this, we noticed that every time we ran the method with slightly different initialization, we would recover different results. So this exact same optimization method, we just initialized, the initial image was just slightly different. In some cases, the bright spot was on the top right, and in some cases, it was on the bottom left. And it appeared that most modes, that both of them fit the data equally well. And so by looking at the data, we couldn't tell which one was the correct image in this case. And so what can we do then with what happens if we use this deep probabilistic imaging approach? Well, we use this imaging framework, this DPI framework, to approximate the posterior distribution, and then we sampled from this network, and this is what we saw. We see that in this learned network, we were also able to capture a posterior distribution that indicates there are two modes in our data. And by embedding our image into a 2D space, we see that most of our images clustered into these two modes, so that it wasn't just like a fluke in our original. But it was something that that required originally when we were using those RML methods, we had to really explore that space to find those two modes. And so here where I'm showing the mean and variation shown to the right for each of these clustered modes. And the distributions of data fitting loss for each image in that mode show that although it can be difficult to tell which image is correct by the inspection of statistics for a single image, if you analyze the histogram of statistics for each mode, it becomes clearer which mode is more likely to correspond with the true image. In this case, mode 2, which does happen to look more like the truth. And so this new variational approach gives us a way to efficiently learn and sample from an approximate posterior distribution. And once we have done this, we can then visualize uncertainty. But perhaps the most interesting is what happens when we run it on some real data. So this is actually a result we got the very first time we ran this approach on the real M87 black hole data. And we did this, when we did this, we saw there were two clusters of results that popped out of the posterior, but the absolute position of the source is actually not constrained in the data. So if you discount the shifting of the ring, they look quite similar, I would say. And so they probably should be classified as one mode up. This is kind of a preliminary result. But what I find really encouraging is that if you compare the standard deviation in the resulting image to the standard deviation we had published earlier, you see that they are amazingly similar. And in particular, both uncertainty maps show that there are these three regions along the bottom of the ring with the highest uncertainty that seem to match up. And so although this is not telling us something really new about the M87 image, what is really exciting to me is that this was the very first time Ha ran this method on the real M87 data, and he got the same result that it took a whole group months to achieve. So I hope this helps us speed up time to results in the future. Okay, so let's get back to M87 and what we have recovered from this image. So in my opinion, we have this beautiful image of the light encircling the black hole. But one question you might have at this point is, what did we learn from this picture? For instance, did we prove Einstein was right? And while I like to say, well, the short answer is no, but we also didn't prove he was wrong, which is also a big deal too. We showed consistency at a whole other level. And so I like to go through exercise of showing you what we can learn from this image and what this ring shape tells us. So for any size object, you can calculate its escape velocity, the critical velocity needed for an object to launch off to infinity. And notice that this escape velocity isn't depending on the mass of the object you're launching at all, but just the mass of the object that you're launching from. And so what happens if the escape velocity is more than the speed of light? Well, then light can't escape and you get a dark star black hole. And so if you take a fixed size mass, you can calculate this from the equation, how much you need to crunch it down to get a black hole. And this critical radius is called the Schwarzschild radius. But actually what we expect to see is not this event horizon itself, but the point at which photons are orbiting around the black hole. So they orbit a couple times before launching off towards us, so we can see that ring. But not even that is what we expect to see. So due to immense gravity around the black hole, as the photons are launching off towards us, they're actually lensed out and the ring becomes bigger. So for a non-spinning black hole, the diameter is 5.2 times the Schwarzschild radius. And if the black hole is maximally spinning, it appears a bit smaller. And so this range of diameters between 4.8 and 5.2 times the Schwarzschild radius is the range that we'd expect to see for a black hole obeying canonical general relativity. And notice that this directly depends on the mass of the black hole. So for a smaller mass black hole, this ring becomes smaller. And that's interesting because actually from past measurements of M87's mass, it was very unclear what the mass was. Gas dynamics pointed us to around 3.5 billion solar masses, but stellar dynamics pointed more to about 6.5 billion. And stellar dynamics provided an upper limit as there couldn't have been more mass within the stellar orbits than from just the black holes, so we wouldn't expect a ring any bigger than this yellow one. But then we could ask ourselves, okay, how do we turn this into a test of black holes? Well, we can look at other unusual and exotic objects. For instance, wormholes also produce a shadow feature, but wormholes have a smaller shadow than a black hole. And there's also things called naked singularities or super splitting black holes that also produce shadows, but they would even be much, much smaller. And so when you lay the Event Horizon Telescope image on top of them all, you instantly rule out all these other exotic possibilities, and you're left with a ring that matches nearly perfectly with the stellar dynamic measurement of the black hole mass of 6.5 billion solar masses for canonical general relativity. So this is one of the many things that we can learn about black holes and gravity by studying this image. But perhaps the most amazing thing that we see is that by comparing this picture to simulations scientists have made for years, we find that the image we have taken is amazingly consistent with a number of these predictions. But you might notice that the simulation I just showed is moving. So is our recovered image of M87 also moving? Well, it turns out that in fact it is. So another interesting thing is that we collected the M87 data over 4 nights over the span of a week. And we independently imaged each one of these images, each one of these data sets, and we strung them together to form a movie. And you can, if you play them as a movie, you'll notice there's some evolution. So I'll play it for you here. It's really hard to see, so I'll play it again. You'll notice that the bright spot is going a little bit forward from the left to the bottom of the ring. I'll play it again. So it's pretty neat that we can see evolution in M87, but it isn't just cool to see a black hole evolving. It actually helps us learn a lot more about the science. And so recovering the dynamics of gas flowing around a black hole can help us in mapping the space-time around that black hole, which helps us learn more about gravity. And it also will help us in learning about how black holes form and launch these powerful galactic scale jets. And so it would be a huge scientific gold mine. And as awesome as M87 is, there's actually another black hole the EHT is interested in that might even be able to help us answer these questions even more. And that black hole is called Sagittarius A star, or Sagittarius star for short. And this is the black hole in the center of our own Milky Way galaxy. And Sagittarius star is teeny tiny compared to M87. So M87 is this ginormous 6.5 billion solar mass black hole. And Sagittarius star is only a measly 4 million solar masses, but it's a lot closer to us, 26,000 light years away. So that means it appears about the same size on the sky. But since it is so small, that means that the gas can orbit around it much more quickly. So whereas it takes 4 to 30 days for gas to make a complete orbit around M87, for Sagittarius A star, gas is spinning around, making a full orbit every 4 to 30 minutes. And so we'd like to recover the dynamics of gas flowing around Sagittarius star, but because it's moving so fast, taking a picture is really challenging. It's like trying to take a picture with a long exposure of someone who's moving really quickly. So it just is really challenging with the telescope array we have now. And so to help us take a better picture, we're trying to design the next generation array, which will expand our network of telescopes from 6 different locations on Earth to many more. And we've already begun building out our array to get more data. So we're adding telescopes. We've already added telescopes from Greenland, France, Arizona. And the one I'm most excited about is we recently got funding to add a telescope at Caltech's Owens Valley Radio Observatory. And Caltech is my new home, so I'm really excited to have a telescope here that is joining the array. But imagine what we could do if we added 10 more telescopes. So maybe, we'll definitely be able to get better pictures of M87, but maybe we could actually make a video of the gas falling into the black hole in the center of our own Milky Way galaxy. And being able to do this, as I said, would be a huge scientific gold mine. But before we just plop down a bunch of telescopes, we need to be really careful because building a new telescope is really expensive. It's millions, usually tens of millions of dollars. And so we should try to optimize to find the locations that will give us the biggest bang for our buck. And so that leads to the last part of my talk today that I'll talk about on new techniques we're doing to use machine learning for optimal telescope design. So how should we go about solving for the locations of telescopes in our next generation array? Well, typically the design of sensors are idealized and considered independently from the image reconstruction problem. And in doing so, many assumptions are made. For instance, ignoring any nonlinearities in the system or complexities in the noise. But for problems where the data is so correlated, the noise is so challenging, it's a huge missed opportunity to not consider these kind of different structures we see in the data. And because these problems are so intimately related, the type of data we're collecting and the way that we approach our imaging algorithms, we really should be trying to optimize them jointly. And so how should we go about solving this? Well, if you rearrange the blocks in this diagram, you'll notice that it looks very similar to something called an autoencoder, where the sensing system is the encoder that produces the measurements or codes, and the imaging algorithm is the decoder. And so deep encoders, where the encoder and decoder are neural networks, are often used for image compression. You probably have seen these around. And in these deep autoencoders, you solve for the weights of a neural network that encodes a picture in a small number of measurements at the same time as a network that decodes those measurements into an image. And in the reconstruction problem, you could use an arbitrary mathematical function that takes you from the measurements to an image for the reconstruction. So we could use a neural network for the decoder. This just has to be something that we could code up, right? That takes us, it's just a function of the measurements that gives us an output image. But unlike a generic deep encoder, the sensing system we build must obey physical constraints. And so we can't just use an arbitrary neural network for the encoder. So how do we make sure that we learn something that we can actually build? Well, He has also been working on this problem in my group at Caltech. And the approach that we proposed is to develop a physics-constrained encoder that we train simultaneously with the decoder end-to-end to find an optimized telescope array that works with an optimized image reconstruction method. So let's zoom in. So from an input image, we can define a forward model of the measurements that we expect to collect. So we have our input image here, which we call in Z, and then we have a forward model that produces these measurements. And in this example, we pretend we have 3 possible telescopes to sample from, color-coded blue, red, and green, and these indicate the measurements that come from the telescopes as these colored dots. And these measurements can be complicated, nonlinear, correlated, and noisy. And here I'm showing all possible samples. So we could pass all these samples off to our decoder for the image reconstruction, but that would mean we'd actually have to build all of these telescopes to make those measurements. So our goal is to choose among them to find the best to build. And to do that, we introduced what we call a sensor sampling distribution that characterizes the probability that we sample from a particular telescope. And we sample telescopes from this distribution, and then we mask out any measurements that are not produced by those telescopes. So for instance, in this case, now just the red and blue dots remain. And every time we sample from this probability distribution, we may sample different combinations of and obtain different observed measurements. And then these observed measurements, we're saying, okay, let's then pass these measurements on to the decoder to recover an image. So we can string all the pieces together into a single differentiable network with trainable blocks highlighted in red here. And so our ultimate goal is to use this network to learn an optimal probability distribution of the telescopes to build. So our goal is to find that sensor sampling distribution that tells us which are the most important locations for us to put a telescope to get the best image in the end. And we do that by maximizing the similarity. We just solve an optimization problem where we maximize the similarity between input and output images. We want to have sensor sparsity to have the fewest number of telescopes to build. And we also include a term that encourages diversity to make sure we've explored the range of possibilities. And then we learn the sensor sampling distribution parameters during end-to-end training. And so what does this sensor sampling distribution, so what is this sensor sampling distribution that we search for? So in past work, one that has worked really well is we model our sensor sampling distribution as a binary, fully connected IC model, which is just a binary Markov random field that indicates which sensors we should turn on and off and how the sensors are correlated. So the parameters are basically ones that talk about how important each site is individually, which is something like a marginal distribution of that site, and then ones that characterize the correlation among sites. So like if I sample this telescope, how likely do I want to sample this other one, or do I not care about sampling this other one? And so this is these parameters theta are learned during end-to-end training that searches for these best model parameters. And so here is an example of a telescope distribution that we have learned. The IC model parameters theta jj on the left are quantifying the activity or the importance of a single telescope, and the model parameters theta jk on the right quantify the correlation between pairs of telescopes. Here, red is representing positive correlations and blue represents negative correlations. And so from these recovered distributions, we can see some patterns that we expect to see. So for instance, in the case of uncorrelated noise, in many cases, co-located telescopes are heavily penalized from sampling together. And that makes sense because they're going to be capturing the exact same frequency component. So why would you want to measure that twice in the case of that kind of noise? But my favorite thing is not the things that we would expect to see, but the things that we don't know what we expect. So for instance, by changing the types of noise we train on, we can also see how this affects our results. So For instance, this is a result where we assume there's only purely Gaussian thermal noise that was included on the measurements. But when we include that difficult atmospheric phase air that plagues our measurements that I talked about earlier, the array preferences actually change fairly drastically. So notice when I flip back and forth that the correlations have changed. And we find this tells us about structures in the geometry that are preferred in the case of this challenging data noise with correlations. And so I find this really exciting because complicated and correlated noise is not something that people can easily consider analytically. You know, this is not something that's considered in, for instance, compressed sensing literature and things like that. So I'm really excited to be able to handle these much more complicated models now and learn from them. But perhaps our goal is not just image reconstruction. Let's say our goal is to extract some sort of feature or classify some black hole property. So for instance, we might want to classify, okay, is the data that we see of the real black hole, is it more likely to correspond with this model of black holes or this other model of black holes? And in this case, our optimal telescopes to sample might actually be different from if our goal is to make an image. If we want to go directly to classification, maybe the information you want to collect is different. And we do see this is somewhat the case in things we have tried so far. So here's an example when we're comparing the imaging task to a classification task. And notice that the activity and correlation parameters of these two cases are similar, but in the classification task, the long baseline telescopes, such as baselines to the South Pole Telescope, seem more active, which is indicating that maybe our classification is requiring more fine structures because the South Pole Telescope probes these really high frequency information. So using this approach, we're starting to understand where we maybe want to place our next ground-based telescopes to reveal more of the unseen. And I'm also really excited that we may be able to apply it to a variety of other scenarios, including even the optimal placement of telescopes in space. But as I said at the beginning, the synergy of sensor design and algorithm development to fill gaps of knowledge can be a really powerful tool in a number of applications, not just black hole imaging. And so this technique I presented for jointly learning a sensor sampling distribution with image reconstruction method or classification method, I think is really general. And so we're also now trying to apply it to other kinds of applications, for instance, microscopy and MRI, and I hope that it will be applicable to a number of different scenarios. And so to close, we have learned a lot from this image of the black hole in M87 already, but what I hope I got across in the talk today is really we're just at the very beginning. Now we have this new extreme laboratory of gravity. We're already thinking towards the future in ways that we can improve our instrument, improve our algorithms, improve them jointly with the help of ideas from machine learning and computer vision and graphics to learn even more. And hopefully one day, not to show you a static image of a black hole, but a movie of a black hole as gas is slowly falling towards its event horizon. And with that, thank you, and I'm happy to take any questions.
Well, thank you very much, Katie. You should imagine a virtual applause if you were presenting live. This was very inspiring, and I hope that people here found it as inspirational as I did. And for the students in the master, even if you missed some of the details, that's perfectly normal. There are a bunch of important messages here in this talk. I'm just sort of giving you a little time to type some questions, by the way. So as I finish my little speech, please go ahead and kickstart the Q&A session. So as I said, for the students in the masters, you just learn basically what computational imaging is, right? You overcome the limits of physics by adding computation. And Professor Katie Bouman showed how first you need a telescope the size of the Earth, which is totally impossible. So how do you work around that? And the key is computation. Another message that I would like to transmit is never believe what you obtain. She said, this is the images that we got, and now how do we know that they are true? Okay, so they started some validation process and they challenged their own results. So I hope you take these messages and use them throughout the year. So I'm going to start with one question, and again, please type the questions in the chat, and Julio, feel free to jump in if there are questions in the YouTube channel. So, Katie, what are the expectations in terms of resolution? I'm assuming that resolution is bounded by the wavelength that you capture and also the baseline of the telescopes. But then you have your machinery, your computation, and now you have your new ways of treating the data that you capture. So, yeah, what are the expectations in terms of resolution that you hope to image that you couldn't do before?
So as I talked about earlier, there is this fundamental limits of how fine of details we can see, and that's going to be based upon the wavelength of light that we want to observe and the angular resolution. So the angular resolution is going to be fixed based upon the size of that ring. So as I said, about 40 to 50 microarcseconds based upon your M87 or Sagittarius A star. The wavelength is defined by a number of things, but when you go to too short of wavelengths, it's there's this kind of like sweet spot. And when you go to longer wavelengths, the gas that's spinning around the black hole is blocking us from seeing that inner ring. So this is, for instance, a simulation of what it looks like, of what we would expect to see if we were looking at about a 3 millimeter wavelength. And as you as you go down to a shorter wavelength, oh, it's not playing. Oh, that's weird. Oh, there it goes. I'll just play it here. As you go down to a shorter wavelength, you can see this ring. Maybe if I right here.
Mm-hmm.
Yeah, you can see that as you go to closer to a 1 millimeter wavelength, that gas kind of, you can see through it, becomes optically thin, and you start to get that ring of light in the center that we're really aiming for. So there's this particular like sweet spot of wavelength of light that allows us to pierce through all the gas and dust, as well as the gas that is spinning around the black hole in the immediate region around the black hole. And so we can go from about the wavelength we observed as 1.3 millimeters, we can go down to about 0.8 millimeter wavelength. And if the smaller we go, the higher resolution. So we're kind of on the larger end of that, and we're trying to push ourselves to 0.8 millimeters. But as you push yourself to shorter wavelengths, being able to actually build receivers to capture that signal is way more challenging. And so this is something in active development. It's about, we're going from about 230 gigahertz to 345 gigahertz, which will hopefully improve our resolution a little bit. But really that kind of is constraining our resolution. Our imaging algorithms actually have been able to, to at least empirically prove, provably through empirical ways, we have seen that they achieve some level of super resolution, but usually I wouldn't trust anything that's more than about half to 3/4 of the resolution we'd expect to see just due to the limits of diffraction.
Yeah, thank you.
I wanted to, like, if I may, I wanted to piggyback on your question as well. Like, I was going to ask something similar. So, given these constraints on the wavelength that you can use to remove all the gas that you have to take out, so it seems like a coincidence that you can, not a coincidence, but it seems like very convenient that you can actually image the M87 because the radius of the Earth becomes exactly the size of the virtual telescope you have to actually use.
It's an amazing coincidence. We got very lucky.
Okay, yeah, but my point is that, like, are there like any other known black holes that or galaxies with black holes that actually match this resolution, or you will have to put some, I don't know, like you will have to make like a bigger lens than the Earth, and then you have to put something on space to capture the things that you're capturing now from Earth. Also, like on terms of this, my second question would be, would it be easier to just try to solve these constraints computationally instead of building a telescope that goes beyond the Earth's atmosphere or the Earth's surface?
Yeah, so okay. So answering the first question, so we got super lucky. It's like this Goldilocks problem, right? Where we got just right of getting the Earth-sized telescope at around a 1 millimeter wavelength. We can just start to see the event horizon. of those two black holes. The M87 black hole, which is 55 million light years away, but it's much bigger, and the Sagittarius A star black hole, which is close to us, but a smaller black hole. So those are the two that from an Earth-sized telescope we expect to see. Most, what people believe is most galaxies have a supermassive black hole at their core nowadays. Nowadays, most people believe that to be the case. And we do image with the Event Horizon Telescope other black holes. They're called active galactic nuclei, other AGN, but where we can't see those event horizons, but we can see the jets coming off of them. And so, for instance, one of the things that we did to validate our image was to actually image one of these AGN and check to see that it aligned with what we thought we should get, and that our calibration errors were consistent with what we saw in the M87 data. So we do image other sources, other black holes, the other black holes out there, but we cannot get with an Earth-sized telescope array down to see that event horizon. So you're right, like we're gonna have to get a bigger aperture size, a synthetic aperture, and that means going to space. So as I said in the one final slide at the end, we're thinking about going to space, and so that you can have a bigger telescope, basically larger baselines that probe higher frequency information. The challenge is, so the Event Horizon Telescope, we got lucky in a number of ways. Another way we got lucky is that we could kind of leverage the work that other people had done for these telescopes. So we kind of recycled. These telescopes were originally built for other reasons, and we just put hardware in it, which was expensive, but it's not nearly as expensive as building new telescopes, let alone a space telescope. So the project was, people estimate $60 million. I think it's probably more than that, but probably less than $100 million for this project. Whereas putting a single telescope in space that would, at this frequency, people I work with JPL now. I'm having a meeting on this actually tomorrow. It's estimated about $500 million to $1 billion for one telescope. And so the question is, if we want to go to space, what should we do? We can't have it's hard to put a constellation when they're that expensive in space. So maybe we wouldn't be able to make an image, but maybe we would be able to do model fitting or we're still in the stage of trying to understand what we could do, but it's much more expensive to do that. But yeah, that is something that we are considering, and I'm excited about that in the future.
Yeah, so probably solving those problems computationally or giving some method that actually can go or take over the baseline that you have. Maybe that should be worth investing on, or
yeah,
the baseline is the baseline and there's nothing to do with that.
You have to be careful, like what Diego was saying, the more that you use your computational methods, the more that you're trying to inject information into the problem. And so you have to become even more suspicious of your results. And so, you can do a lot computationally, the stronger your model is. But then you're saying, okay, I'm getting these results under the assumption that this model is correct. So you always have to have that kind of disclaimer. But I do think that the important is pushing both directions. Yeah.
Okay, great, thank you.
So there are a few questions here. I'm gonna join the first two, which are similar. Are there other elements in space you're planning to capture now with all these telescopes and the computational imaging techniques you've mastered, or other elements you think this might be useful for? And as I said, there is a second question, which is similar. Can you use this for capturing similar phenomena? Or, as you said, wormholes in particular?
Yeah, so we are, as I mentioned, using the Event Horizon. Well, first of all, the technique. The technique is actually applicable to other kinds of telescope arrays that are not the Event Horizon Telescope. There are basically any radio image you've seen. So any image, astronomical image that use radio wavelengths is using this technique, because people pretty much cannot build radio telescopes, single-dish radio telescopes that are big enough to see of anything that's really exciting, I would say. And so most of them do use some sort of technique, but they're usually using techniques that were developed a long time ago. And so we are pushing to incorporate these techniques into common practice for people to make other radio telescopes, to work with other radio telescopes and extract more information from those images. As far as the Event Horizon Telescope, we are interested in, as I said, we've imaged other kinds of sources. For instance, these other black holes and other galaxies where they have these galactic scale jets that are coming off of them. And these are things that we have never seen at these wavelengths and these resolutions. And so there's a lot of really interesting things and exciting things that we've been studying with them, some that are in the works. So I can't talk about details that much, but it's cool. They're not, the black hole event horizon is kind of the most exciting thing, I would say, for the for most people. But I think that these other sources also tell us a lot about how black holes interact with their host galaxies and other just interesting, exciting things. As far as and then when we go forward to so right now we have this big NSF grant, a National Science Foundation grant for expanding the Event Horizon Telescope, and we're in the stages of designing that telescope. So it's mostly focused on extracting information from the black hole, but there's other things from the black hole that we haven't been able to image yet. So as I talked about, there's the Sagittarius A star black hole where you can't see the evolution. So we'll hopefully be able to make a movie. And then also I talked about this jet that is coming off M87 that was actually the first thing that was discovered over 100 years ago. But because our telescope is so focused on getting that ring, it's kind of completely ignores the large scale structure that attaches to that ring. So it's kind of like taking your camera and zooming in on a bird that is flying in the sky and missing the fact that there's clouds all around it, right? And so we're hoping that as we add new telescopes, it doesn't just allow us to make a movie of a black hole, but actually allow us to see how that black hole, that small scale black hole, is connecting to this big scale features around it. And then we learn a lot from that. So there's other astronomical sources, definitely. One last thing. So the ALMA telescope in Chile, which is the most expensive, the most powerful radio telescope in the world, is about 60 telescopes that all work together, and they image lots of really exciting things like protoplanetary disks, which is where the planets are forming in their solar systems, and they're carving out these rings of dust that are beautiful to see, and that we've used our method to apply to these. I'm also working with a group here at Caltech on a new kind of telescope that's being proposed called the radio camera, or the DSA 2000, which has the opposite problem with the EHT. The EHT only had less than 10 telescopes, right? The DSA 2000 has 2,000 telescopes that they're proposing. The problem there is that they're going to have so much data. They get a terabit or 5 terabits a second of data. And so the challenge there is, how do you deal with all that data? And you can't use these complicated optimization methods for it, but we want to be able to really quickly image the night sky and see transients and use it to help identify exoplanets and fast radio bursts and different things in the sky. So yeah, lots of different kind of directions, but each of them has their own particular challenges.
Yeah, pretty exciting. Thank you. Joanna asks, about the movie of the black hole, you said that the period of the black hole was up to 30 days, and you seem to have captured data for only a few days. Mm-hmm. How costly will it be to capture images during the whole 30 days to observe the full period, or maybe there is no interest in doing that?
Yeah, lots of really good questions. So yeah, we observed the M87. So first of all, depending on how fast the black hole is spinning, you'll have a complete orbit of gas every 4 to 30 days. So it's unclear if it would be on the 4 or on the 30-day time span. But yeah, we observed over the course of a week and 4 days over that course of a week. So it was like at the beginning. So we had some days at the beginning of the week, some days at the end of the week. Observing right now is a huge cost. Or whatever. First of all, we have to propose for telescope time, so we even have to win time to observe the sources. And then we have to people go out to the telescopes and have to collect the data over the course of weeks. So I went for 3 years, about 2 weeks every time to collect that data. It's not something that you can trigger from your computer right now. And the reason, and we choose every year at a certain time in April or late March, early April, because it's the best weather in the telescopes. So this is another thing I didn't even talk about. And so we have to make sure we're coordinating so the weather is good at all the stations. It's a really like we're really counting our lucky stars to hope that we're having good weather at all these telescope sites. And so that time of year is the best where we're most likely to get good weather. But as we go and we start adding more telescopes, we are hoping to be able to remotely operate these telescopes, and that there would be enough telescopes online depending on the weather so that we could observe more frequently. So that is a goal of our future of designing the array out, that we would be able to observe throughout the year so that we can map the gas falling around, because that is really important to be able to map those dynamics. So yeah, great question.
Thanks. Just to change the pace a little bit, there's a master's student with 2 more personal questions. I quote, many students are right now deciding on a field of research. When you started to specialize in computer imagery, computational imaging, I guess, was it something you sought specifically for personal preference? Was it something you were offered? How did you make that decision? And the second question, is there any advice you would give yourself before starting this research adventure? So yeah. I read again, was it something you sought specifically for personal preference? Yeah.
Yeah, I think that it wasn't. Definitely the black hole thing, definitely not. I'd say that was something totally stumbled across. The computational imaging, I would say that I got excited about images when I was in undergrad. I would say I actually even in high school, I was really interested. At that point, I wanted to do psychology of human perception in color and stuff. I was really excited. I did the science fair project on opponent colors, and I was really into it. And then based upon that work, I got a lab job in a university that I was helping a graduate student collect their data. And it was an image processing and image and video processing laboratory. And that's where I was really introduced to images and how you can manipulate them and how you can extract hidden information from them. And I thought that was really cool. So based upon that, I decided what I wanted, that I wanted to go do research in computer vision or image processing kind of area. And I did, and all the people in this group were electrical engineers. So I decided I guess I should be an electrical engineer if I want to study images. And another thing is I think what I liked about images is that I could visualize you could visualize what you were working on. And for me, I think a very visual person. So that was I really liked that. And so then I decided, okay, I went to a computer vision group. I worked in a computer science and artificial intelligence lab at MIT. And this group kind of straddled, I'd say, it's more on the computer science side, but it did straddle signal processing, electrical engineering, material a little as well. And at first, I really wanted to do object detection. And because that was such a cool thing. And so after my first year in grad school, I decided to do an internship at Microsoft Research on object detection. And it was really great. I learned a ton in that internship, but I also learned that I don't like object detection. And I learned, and I kind of kept gravitating towards inverse problems, which I think did have a little bit of inspiration from my background in electrical engineering, I like these inverse physics-based problems. And so, yeah, I think I wanted, I was in the general area of image stuff, but I definitely, as I got older, gravitated more towards this idea of computational imaging. I think I didn't even realize this phrase, computational imaging, until I was applying for jobs. I still, this is something that has definitely developed over time, and I'm still developing it and trying to learn what do I enjoy and what do I love working on. So yeah, no, I think, just follow the path of things you enjoy. And as far as, what was the second? It was advice that I give myself?
Yeah, is there any advice you would give yourself before starting this research adventure?
Yeah, so I would say when I started this project, I was very nervous, the black hole imaging project, because it was off the mainstream from computer vision, which is what the area that my group was in. And because of that, I did hedge my bets a bit by working on other projects at the same time. But I'm really glad that I took the leap with working on the project because, and I think that, you always have to take risks. So you always have to manage your risk, right? But don't let people tell you, if you find something really exciting, just like go and do it. And like the things that you're most excited about, you're going to do the best on because you're most excited about making them work out. So, be smart about it, but go after things that maybe seem impossible or people don't necessarily encourage everyone to do because it's not the mainstream of things. So that's my advice, I would say. Explore.
Yeah, I think it's an excellent answer, excellent advice, and that's a question that we get a lot here as well. And to David and to everybody, don't be so afraid of making the right decision now. As she said, just find something that is interesting for you. You're 22 years old, something. You can make mistakes. You can change your field of research. Things will happen. One thing will lead to another. Don't try to have the whole future planned in front of yourselves. Just find something that is interesting. See what happens. Thank you. There's a few more questions. I'm going to start with the master students first, and then. So Diego here says, why are some areas around the black hole brighter than others in the image? Shouldn't the light be equally distributed, or is it just due to the gas?
Yeah, so it's because also a good observation. So when you are so there's gas. You have a black hole. You have gas spinning around the black hole. This is called the accretion disk. And when you're looking straight down at the black hole, when it's face on, the gas is all going to be equally bright. But actually, as you go more and you're looking at it more edge on, when the gas is moving towards you, it's going to be brighter because it's Doppler boosted. So because it's moving so close to the speed of light, as it's coming towards you, it becomes brighter. And on the side when it's moving away from you, it becomes dimmer. And so this is going to cause an asymmetry in the brightness along the ring. And so the M87 black hole is pointed almost nearly face on to us. So, I said face on is when it's perfectly, it's like just going in this plane, but it's actually at about a 20-degree angle, 17 degrees. And so that means it's off a little bit. And so that means the gas on one side, it's going to be coming slightly towards us faster. And on the other way, it's going to be going away from us. And so from this, we actually realized, using your right-hand rule, that the black hole that is spinning away from us because the gas on the bottom is more likely, it is brighter. And so that means it's more likely to be spinning away from us. So from this, we got this scientific, we were able to extract the science that we didn't know otherwise. And one fun fact is Interstellar, which has an amazingly accurate model of a black hole in it. This Gargantua, which I don't know if you guys have seen it, but it was a movie that came out in 2014. This is the one feature that they took out of the simulation. They decided that it was too hard for people to understand this Doppler boosting, and it wasn't as artistic. So actually, they removed that from the simulation of the black hole. But other than that, it's a pretty accurate simulation of a black hole.
Yeah, sorry. Thank you. Linked to that last question, there was another one saying, could it happen that due to the bad positioning of the black hole, you could not visualize the image?
Sorry, say.
So could it happen? Could it happen that due to a bad positioning of the hole, I guess, the jets not being perpendicular to the plane of the camera, of the virtual camera, could you not visualize the image?
Yeah. So no matter which direction you are viewing the black hole from, because of the fact you have this black hole and it's bending the light around it, you're always going to get this ring of light, and it's always going to be roughly the same size. What is happening is, when you have that face-on black hole, when the gas is moving like this, then it's going to be much easier to see that ring. When it's edge-on and it's much coming faster to you one side much more than the other, that is going to cause that's going to cause more of a crescent shape. like a moon that is a crescent moon kind of shape, and that means it's going to be hard to see the entire ring. So even though that ring is there, it's very dim on the other side. So the more edge on the black hole, the harder it is to see the ring. And so with the Sagittarius A star black hole, with the M87 black hole, we knew the direction because we see these jets. So we knew that it was going to be almost face on. With the Sagittarius star black hole, it's very unclear right now if it's more face on or more edge on. And so that's something that is a challenge, because if it's more edge on, it's going to be harder to see if that ring is there. And then, what was the other point I was going to make? I forget the other point I was going to make. Yeah, so yeah, if it's more edge on, then it's going to be harder to see. Oh, one thing. Okay, but there is an advantage to dealing with something that's more edge on, where it's more of that crescent shape where you can't see the whole ring. The more edge on, the more gravity is going to, like the spin of the black hole is going to affect the shape of that shadow. And so it's easier to see the effects of gravity on that shadow shape the more edge on. So it's kind of like you want a balancing act. You want something that's kind of in the middle, I guess. So we can learn more about gravity, but also get an image. Yeah.
Thank you. Sandra asks, what would you say was the biggest challenge, were the biggest challenges and advantages of working with such a big multidisciplinary and international team?
Mm-hmm. So it's a challenge. I mean, imagine, I don't know how many of you guys have tried writing a paper yet, but imagine writing a paper with 200 authors that have opinions. Right? So it's a challenge, and it's a challenge with time zones and everything. I get up most of my days I have 7 a.m. meetings now, because make sure we all are able to be together and reasonable times. But I think it is really important, because I think as much as there's much as there is back and forth with it, this makes our results better. It makes us test ourselves more. It makes our results stronger. It makes us validate and make sure that we're not putting something out there that we don't believe. So I truly believe that having a big group is essential for distilling our results to something that was really correct and that we have that we're very proud of. And also we needed a big team. I mean, there's tons of parts to this project. There's the instrumentation and developing the telescopes and the instruments in those. There's the computational part that I worked on more, that is, analyzing the data we collect. There's also the theory side of people who are predicting what should we see and how should we develop our instrument and our algorithms to best recover the kind of information we want to see. So there's many different kind of parts of the project, and we needed people to come at it from different sides for us to kind of get the best result. So it is a challenge, but it is I think a necessary challenge. And I think this is somewhere where I think big science is moving more in this direction, where we have to bring people together with different kinds of expertise to pull more, to squeeze more out of the data that we're getting. So and I guess one good thing is I was very used to telecons beforehand because of all us working across different countries and stuff. So maybe this COVID pandemic I was a little bit prepared for it and how to deal with online telecon. So I guess that's an advantage.
There you go. Well, thank you. Julio, I don't have any more questions here. Do you have any in YouTube?
I don't think there's any questions here.
Okay.
I was just I wanted to say, I found it very interesting the last part when you were trying to image something with the design of the sensors. So what are the constraints you have? So I guess that there are more constraints when you build the sensors than when you build an algorithm that turns out measurements into the final image that you reconstruct. I'm just curious on how much freedom you would have. This is a broad question, but how much freedom would you have, designing the sensing steps or the sensing pipeline in that, because it's not an easy thing. You have to build a huge telescope that may be purposed for more things than just measuring black holes.
So like I said, the big challenge with that is being able to build in physical constraints, because we can't just build some mathematical function that we've come up with, right? We had to search over viable telescope designs. And so this is an area that I'm really interested in, and we're doing a lot. There's a lot more to do, but this was an initial approach, and what we were doing is turned it into a sensor selection problem, a telescope selection problem. So you'd say, of these 50 telescope sites that are places where we could put a telescope, where are the best 10 to put down? And so that was, we formulated the encoder as selection among these different kinds of measurements we could have. And that allowed us to restrict ourselves to things that we could actually build. We also put in things into this, like you could put in into the energy optimization, like the cost of building a telescope there, or we also put into the forward model things like weather constraint, not weather constraints, but like predictions of how the weather would be and how that would impact measurements and stuff like this. But so we turn it into a selection problem. But that being said, there aren't that many telescope sites on the Earth to choose from. It has to be very high locations to be able to see this really short radio wavelength. And so there aren't like a ton of places we can choose from. And that's why maybe going to space is another reason. Another reason we have more flexibility.
Okay, great. Thank you. And thanks for the awesome talk.
Yeah. Well, I think that's it. It's 7:30, which is about the scheduled time. Thanks a lot. It's fascinating every time. I'm guessing you've given a talk about this topic, like, I don't know, 50 times at least in the last year. Every time I see you, it's like the first time. You're so enthusiastic and passionate about your work. And that is contagious. And thank you very much. So it's been great. I hope you guys have enjoyed it as much as we did. And Julio, if you want to say some closing remarks, or we can just say goodbye now.
I think we can just say thank you and goodbye. And I don't have any other.
Thank you.
Thank you very much.
Thank you very much.
Thank you. Okay. Bye-bye, guys.
Bye-bye.
Bye.
Thank you.
Thank you so much.
Bye.
Bye.
Thank you.